Okay, guys, we may have come across the names of PDKs, like different names, the way they uh, give the whole name of the PDK, right? Sometimes it becomes difficult to decode what exactly are they trying to convey with this name. So here, well, let's try and understand the naming convention of a PDK. So, for example, all in all, if you see, right, from until 20 nanometer, it is planar, and from 16 nanometer onwards, it's a FinFET process. Say, for example, over here, if you have come across a 90 nanometer PDK, you would see on the file that it is GPDK 90 nanometer. Okay, what it tries to convey is it's a generic PDK with a 90 nanometer gate length. Okay, this is a very simple way of defining a PDK. Likewise, you would have different names like chartered 40 nanometer or some, a different foundry, different name. Like that way, they would have used the nomenclature and the technology. Now, if you go into a little more advanced detailing, right, a proper foundry, okay, global foundry is 40 nanometer, low power, 9 metal process. Okay. What it means is it's a global foundry PDK which is at 40 nanometer gate length, and it is designed for low power applications, and it has got 9 metals for you to do your design, out of which 8 and 9 are for power rails, right? And the remaining ones are for your device connections and your logical connections and so on and so forth. So likewise, let's take some other example, say Samsung 14 LPP. Here what it means is it's a Samsung Foundry 14 nanometer. LPP stands for low power plus with EUV extreme ultraviolet lithography. What it means is like it is a 14 nanometer low power PDK, wherein for fabrication process they are using a latest technology called EUV extreme ultraviolet for lithography process. Right now, this is one of the advanced mid-level version, you can call it. So likewise, if you Google it up, and you will be able to find that the predecessor of LPP is LPE. It's like initial version, you can call it. Low power early. It's a kind of first generation low power 14 nanometer PDK released by Samsung, okay, for low power designs in 14 nanometer. Okay, likewise, we have LPP, which we have just spoken, and LPU. Like, generally the way they write is Samsung 14 LPP or 14 LPU, 11M or 13M or something like that, right? So it is low power ultra. Again, they would have made some changes in the fabrication process or the metal features, the doping concentrations and all of that to improvise the power related factors. And say, for example, if you're dealing with the SOI process. So here it says fully depleted SOI process, 14 nanometer or 7 nanometer, whatever, and 11 metal stack. Okay. What it means is like it is given you 11 metals. So likewise, there is a connection between the process. Generally, they write the name of the company first, and then the technology, then the technology node, and the metal stack. Okay, every company has its own way of putting across things, but I'm just trying to put across the generic way so that you can at least be able to correlate the terms and understand when you come across a PDK. Say, for example, TSMC. TSMC says 7 nanometer. 7N is the next improved version of that. And 14 metal stack, 16 metal stack, 11 metal stack. And say chartered semiconductor. Okay, chartered semiconductor has got its special RF library, which is at 45 nanometer, and it's a 13 metal stack. Okay, all the while I've been saying metal stack, 11 metal stack, 9 metal stack. So what exactly is this metal stack, and what is the correlation over here? And when you open up a PDK or dig into the folders, right, of PDK installation or the DRM, you would find some more details. Okay, let's try and understand what's the relation between the metal stack and the name of the GPDK or the PDK over here, right? So here, let's take the first picture. You see that there is a substrate over here, there is a device formation, there is a via contact, sorry, and the metal connection. Via metal 2, via 2, metal 3. Here, let me put a cursor over here. It's not visible. Highlighter, yeah. The device, gate connection, contact, metal 1 via metal 2, metal 3, and then goes the higher metals over here. This is how the fabrication is done. Metals are laid above each other in a stacked form. That's why in the generic term it's called as metal stack, right? If you see here, the lowest metal has got the minimum width, right? As you go further, these two have got same width. This one is slightly wider, you know, and then slowly 9 and 10 are much wider. A simple question over here would be, why do you think they have increased the width of the metal and the thickness of the metal as we go above, right? Because lower metals are used for local connections, and this width is sufficient to carry the required current and to build the logic within the given region for a standard Serralo logic. As we go further, the logic increases, right? And obviously the routing will be more for higher metals, right? From one module to another module, right? From one module to another one, right? Say you have used metal 3 until here in this module, and there's no place for you to use metal 3, right? You have to use metal 4 to pull out the connection. Or something, say the logic is full on, you have to pull out the connections in metal 4, right? Something of that sort. And obviously the distance, what the signal, there is a signal going from this module to this module. There's no place over there for you to use metal 1, 2 or 3. You have been left with no choice to use metal 4, right? And obviously if it's traveling a long distance, there'll be more resistance to it. So how do you deal with such scenarios? So is you have an option wherein the minimum width of the metal is also wider, as well as the thickness of the metal is also more compared to 1, 2 and 3, so that the resistance is less and the signal flow is a lot better. Right? So this is the generic way of explanation. Right? If you see here in this picture, this is an example of a SOI process. Be it any process, the device thing will change. But if you see these metal stacks over here, all of these over here, you see that M1, M2, M3, M4 are of the same width, same thickness, same width, right? They generally define it as 1x, something which is the very first metals. They define it as a standard reference uh, metal width, 1x. Okay. So now, if you go a little above, 5 and 6 are double the thickness, 2t. Okay, double the thickness, and obviously they'll be slightly double the width also. Okay, so that's what here we are talking about the thickness. That's why it says 1t, 2t, 3t, 2t and 4t over here, right? And it says 2x metals. What it means is like 1x is there are 4 metals with 1 width. There are 2 metals with 2x width, which is double the width of this. These two are double the width of this. Say this metal strip, metal 5, is the double the width of metal 4, or metal 3, or metal 2, or metal 1. And that's why it's saying 2x, twice width. You go to 7 and 8, right? It is thickness is there 14, but 4x. It's not taking the reference of this, it's taking the reference of the very first metal. What is drawn over here? It says 4x. This M7 or M8 is 4 times wider or thicker as uh, metal 1. That's what it's trying to show. And if you see here, over here as well, the via sizes also keep on varying. Until here it's the same size. But after here, the width of the via, the size of the via is also increasing, right? So if at all you have to give the name, a proper complete name of, say, let's assume that this is some XYZ, you know, XYZ PDK. Okay, and it is 10 nanometer underscore 10 nm and underscore what do you call, uh, or you can say You just put it SOI, okay? Or we'll say SOI 10 nm. Okay, let me just undo this. Okay. XYZ technology underscore SOI 10, okay, 10 nm you can put, or 10n or something like that, underscore, okay. The way it goes is 4 1x. The way you got to read is there are 4 metals, 4m 1x, or you can say 1x 4m, right? Which means there are 4 metal of 1x width, and they are 2 metals, the next 2 metals. Okay, the way you got to read is the next 2 metals are of 2x width. Just looking at this picture, you can correlate. Say it is, just assume that it is XYZ technology. It is a SOI process. Let's assume that it's at 10 nanometer. What it means is the first 4 metals are of 1x. The next 2 metals are of 2x underscore. And again, the next 2 metals are of 4x. This is for 8 metal. If it is 12 metal, right? Then the next 4 metals are of, you can put it 8x. That's how you got to read the whole name when you dig into this PDKs, right? When you open up the folders, or when you open your library manager kind of a thing in your layout tool, you might come across this. Right? Or probably CAD guys would know that. Or if you have access to it, you can have a look at it. That's how they define the naming, and that's how there is a correlation between the company name, or this thing, foundry name. This is the technology, and the technology node, the metal stack it is used. So what it means here is, so every design will not be that big, right? The architect, the senior designers or whatever the architects might be based on their experience, they would know that implement this logic, 8 metals are more than enough. Okay, within this given area, it all comes by experience. So then they would go and buy a PDK, right, which is of so and so technology and all, for which is having 8 metals, right? If the design is huge, more logic, more bigger, yeah, you buy it for 10 metal. Depending on the number of metals, also the cost of the PDK changes. And so if you're buying 4 metal, the cost is less. If you're buying 8 metals, because the processing steps are more, then the metal use is more, right? The effort put in over here to fabricate higher metals, build in higher logic is more. It's very obvious and straightforward, right? Depending on that, you select. And also even in this, you will have variants like SOI, LPP, or LE. You don't know, whatever the technology, the way they uh, represent their technology advancements or whatever, they would incorporate that also in the name. So this is a simpler way of I'm trying to explain you here. This is how the metal stacking, the foundry name, the technology and all are, that's how it's represented in short. Right. Let's take here, if you see here, these are FEOL, front end of line layers. These are the layers which are used for device formation. BEOL stands for back end of line. These layers are used for metal connections. And that's what it means here. And if you just see an example over here, for 130 nanometer, you had around 6 metals of same width. That was the technology earlier. But for 90 nanometer, obviously this is 5 plus 2, 7 metals. Right? And here if you see, these are 2x. And here if you see 65 nanometer, there are 4 metals of same width, 3 metals of double the width, and these 2 metals of double the width of this. So if I have to write the metal stack naming convention for this, it would be 4m 1x for this guy, 4m 1x underscore 3m, which is the next 3 metals, the next higher 3 metals are of 2x the width, And then the last other two metals, like say next to N, next two higher metals are of 3x below, yeah, 4x below. You can put it. So depending on that, like likewise, you can give the naming for these higher metal stack at lower technology nodes. So all in all, this is how a naming convention is done. I've tried to put it across in a more simplest way so that the students also can understand and the initial working professionals can understand. There is a lot more to the naming convention and a lot more details can be decoded out of it, but just for simple beginners, for people to understand what it means, this is more than enough, and obviously you can build on that. Okay, so in the next session, we will try to understand what is a DRM, who uses that, and how to read it. All of that we'll study in the next session.